So, you've committed to terraforming a new world, to creating gardens where once was only a dead planet. But even with a plan in place, the challenges ahead remain just as daunting. It is a task of not just a lifetime, but entire generations to come. A lot of times when we talk about traveling to new worlds and transplanting humanity there, we imagine seeing some domes covering some blasted and desolate terrain in the early days, and then later seeing forests and gardens all over the planet. Getting from point A to point B is a big topic, and today is an informal sequel to last month's episode on early terraforming, though you don't need to have watched that first, as we'll repeat some of the necessary basics. Though I want to poke deeper into the details today. Often, when we discuss space habitats, we talk about how much easier they are to create ecosystems in than terraforming a whole planet, but the details tend to be scarce. There's an old South Park joke that comes to mind in regard to socks and undergarments tending to disappear in the laundry, where the characters discover where their clothes have gone missing and why. Kinda. It turns out gnomes have been stealing them to resell them, and their business model consists of a simple 3 steps. Step 1, steal the clothes. Step 2, and Step 3, profit. Step 2 is mysteriously left blank, and the gnomes seem to avoid answering when asked about it. I often encounter this with various organizational, mission, or business plans, though usually more concealed, and a lot of times it's because the folks involved aren't even seeing that missing step. High-tech and futuristic scenarios often have this too, and indeed a lot of our Alien Civilization series episodes poke at complex alien motivations or goals for having a lot of gaps that aren't explained or are filled with one option arbitrarily and exclusively selected when many others would have seemed available. The aliens want something we have and invade, rather than pursuing other places to get it, or just bribing us with some piece of technology. Or even just dropping a mountain on us, instead of invading with foot troops and space fighters. Ironically, dropping mountains on planets might be a common terraforming tactic. But it is often a justified blank space, because while we would love to know the details of setting up a biosphere in, say, 50% of normal gravity, we have no data on ecology in half gravity. We have a very limited amount of data of biology in 0 gravity, but none at low gravity of any kind. Just a few days of low gravity data on those 12 humans who spent some time on the moon, which was bookended by a stressful journey of both high acceleration and microgravity, so represents very little data and very noisy data at that. We have tons of information on regular gravity ecosystems, at least on Earth. A planet with our gravity but different lighting or day or year lengths would have very different ecosystems. And just consider the variety here for a tundra versus a tropical island or a deep sea trench. Still, we have every reason to think you can have ecologies in half gravity, or a 27-hour day, or a 90-day year. But until we've got some hands-on real experimental data from such places, loose guesstimates are the best we can do. And given that orange and red dwarf stars vastly outnumber yellow stars like our own, and that their habitable zones are likely to be limited to orbital periods of weeks or just a few months, not a full Earth year, the answer is going to be very important, as 90-day years are likely far more common than 365-day years for potentially habitable planets. Nonetheless, while we need to know, we don't yet, and answers are pretty speculative. I wanted to put that on the front end here because we'll be talking about some grand projects that dwarf anything we've ever done before in complexity, literal world building, forging whole new ecologies. I believe we can do this, but we must also have the humility and honesty to acknowledge up front that we will be stumbling amateurs at the beginning. But with 1 trillion planets in the galaxy we can probably make livable, and untoward quadrillions of space habitats we might build and plant ecologies upon, I tend to think we'll master it from experience and practice, if nothing else. With that said, we do need to understand that we are not keeping one person or critter alive, or growing some food crops in some hydroponic bays. We are talking about building up the biosphere from the ground up to the sky, and literally too, as we need to create soil from barren and possibly toxic regolith, and alter or add the sea and sky. And for space habitats, we must build the big cylindrical outer skins, spin them up, and add in the sunlight by mirrors or reactors, and then plant land, sea, and sky inside them. By default, our two ground zeros for starting a biosphere are either a big dome or a giant spinning can, but in practice it will begin with a petri dish. Your typical gram of soil has billions of bacteria in it, and an estimated 60,000 species of them. While it's always possible we might engineer some vacuum-resistant species of bacteria in the future that we could just drop on dead worlds, I think it is more likely that you would be taking lots of local regolith samples, crushing them up, and adding water and sunlight and some packets of bacteria and other microorganisms to see what did best first in each scenario. The thing about an ecosystem is that it's composed of millions of different parts that have a loose state of equilibrium. That equilibrium is only ever temporary, but millions of species next to each other in our environment have adapted to each other, and even the weaker species on the edge of extinction were previous grand champions at the game of life, at least as played on Earth. During the human era, we got a lot of evidence how fragile those equilibriums really are, and on an alien planet or dead rock, this will only be easier to see. If one type of microbe does vastly better than others, that might be fine, so long as all the necessary ecological chores are getting done, but otherwise we need to be supplementing that ecology in ways that keep those others competitive. Or genetically tweaking them to do so, or finding another terrestrial microbe that might do the job and perform better in a rearranged ecology. You may even use mechanical aids, like giant air scrubbers to fill the role of creating free oxygen. A biosphere may have artificial components, after all, ours already do. We also need to emphasize that we aren't planting modern Earth from day one. Not only are we starting with just those most basic elements, a microorganism ecology like Earth had for most of its existence, we are probably aiming for the microorganism ecology closer to that of an early Earth, not our modern one. That does not mean we need to wait a couple billion years to introduce modern large flora and fauna. Those microorganisms have generations measured in days or even hours sometimes, and you would have no problem going from a petri dish to a plant-sized microbe tank in a single year if you were giving assistance at helping it quickly migrate and preparing the land for that. I'm not sure even an actual petri dish the size of a planet, or Discworld, with complete nutrients, would actually get covered in a single year if you weren't moving the contents around, since that would require a spread of something like a mile or kilometer per hour, when bacteria, under their own motive power, generally move at more like a meter a day, and that's probably more of a random walk. At a speed like that, even assuming they could eat and grow into new space freely, and propagate in wet soil or regolith even that fast, as opposed to an ideal petri dish, you are talking tens of thousands of years. Exponential growth can be terrifyingly powerful, but reality tends to put in its own constraints. A single amoeba undergoing mitosis every day can become as numerous as the human race in about a month, outnumber the stars themselves in under 3, and then would outnumber the atoms in the universe in about 9 months, the timeline it takes to grow a single person. We need longer to double, more like 20 years a person, but that means we would outnumber the atoms in the universe in just 5,500 years. We've been around longer than that and do not, and the reasons are many. And as fast as we can reproduce, we still have to journey to empty planets to colonize them or to gain their resources to build space habitats from. We are constrained by the speed of light, and indeed would have to work hard to get to even 1% of light speed. It can be easy to forget, after contemplating timelines of potentially hundreds of years to travel to a new star, that you might need at least that long just to get that planet as inhospitable as a desert, let alone an Eden-like paradise. And of course we have spaceships for such efforts, not just our own 2 feet. The bacteria usually have a small flagella. Of course they can move faster than that on Earth, but they are being carried by the environment or some larger and faster organism that they're hitchhiking on. You've probably got no sea or sky to blow them around to the 4 corners of your new Earth, or the 2 poles and the equator of a new planet, or the cylinder caps of an O'Neill cylinder or the polar circles of a Stanford torus, and no critters to hitchhike on. Very different native weather on unearthly places, and we'll return to that. But given that the initial conditions for life won't be available and will be slowly added, you also likely have at least two different ecologies going on. Those under the domes or in the labs with controlled conditions similar to Earth, and those in the uncontrolled outside that can survive the early environment once you get to the most basic livable state. And as a reminder, life can adapt and quickly to some really awful environments, possibly even the outside of the space station near air leaks, or maybe cracks in a dome on some dead planet. Odds are good a lot of planets we encounter will have water, heat, and air already on them. Those we build will presumably have it pumped in from early on. We tend to assume we bombard dry and airless rocks with comets, and then we build a spinning habitat, then drag some small asteroid or comet in, seal the cap, break it apart, and let it fall down to spread out as the habitat spins around like a washing machine on spin cycle, only much slower. Your washing machine isn't generating 1 g-force the way the habitat presumably is. It's more on an order of 100 g's in your washer. We shouldn't be assuming we only build one biosphere. I don't mean that a planet or a habitat might have many different ecosystems, but rather we're introducing new strains of microbes as we go, while others will probably get pushed from early dominance to weaker levels as we introduce microbes that can, for instance, eat them. They are all microbes living even in deserts and tundra, and these are probably your good early candidates. But don't assume their hardiness means they compete well in other environments. They are not a superorganism, they are a well-adapted organism. But that adaptation might make them useful early on. Indeed, these extreme condition organisms living on the dead fringes of our planet might be the pioneers of new worlds. The Atacama Desert in Chile, known as the driest place on Earth, though technically second after the McMurdo Valleys in Antarctica, has some interesting ecology going on there. Not much ecology, the biomass is terribly small, and it essentially never rains there, but it is the driest example of what is known as a fog desert, a place where what life exists gains most of its moisture from fog. And if you remember the moisture farmers of Tatooine in Star Wars, the desert homeland of the Skywalkers, this is presumably what they were doing too. We see something similar on the desert planet of Arrakis, also known as Dune. I think you would see sealed dome environments on barren planets, but as you brought in moisture and air, you might start making mini small tanks you could drop off, or even kick out of an aircraft with a parachute on, that were intentionally leaky terrariums with some moisture harvesting apparatus and a lot of fog desert organisms. Those aren't necessarily all microscopic either. There's a beetle that lives in the Namib fog desert, the Stanakara beetle, that is able to survive by collecting water on its bumpy back surface from early morning fogs. The beetle faces into the breeze at a 45-degree angle, and captures fog droplets on its hardened wings. Its head faces upward, and its stiff, bumpy wings are spread against the damp air. Tiny droplets, 15 to 20 micrometers from the fog, adhere to the hydrophilic bumps on the wings, surrounded by waxy hydrophobic troughs. These droplets flatten upon contact with the hydrophilic surfaces, preventing them from being blown away and allowing other droplets to attach. As the droplets accumulate, they eventually grow large enough to overcome electrostatic forces and roll down the beetle's back to its mouth parts. Thus it can survive, if not really thrive. Such a creature could then feed, say, a rodent or bird, and whether or not you even need such flora and fauna along the way depends on how long it's taking you to bring in water and air. Of course, even those fog deserts have more humid air than Mars does, so you do need to bring some in, and you really do not want to rush with this. As we mentioned before, Earth averages a few miles deep of water in the ocean, and even if it was raining a foot a day, it would take several decades to fill such seas. And that's assuming that was all new water coming in from space, not rain from local evaporation too. As we've also mentioned before, a comet coming into a planet is moving at a speed equal or greater than whatever that planet's escape velocity is, probably on an order of 10 kilometers per second, which is implying a kinetic energy of at least 50 million joules per liter of water, half again the energy released in burning a liter of gasoline. That water is hot. Ask the dinosaurs how good an idea it is to pummel a planet with objects kilometers across, and keep in mind that their asteroid is thought to have had maybe 1,000 cubic kilometers in it. Our oceans are a couple million times that size. This would be comets, not asteroids, to give us water, and probably also ammonia and methane, not rock. But while that helps, it does not eliminate the problem. It is also hard to emphasize how much energy it would take to move those icy bodies to a planet, even if careful nudging meant you only had to provide maybe 1% of whatever that final kinetic energy was. Let's imagine that big interstellar ship that brought the colonists there could be refueled and running its engines, or sails and collectors, at something like a terawatt of power, which is huge. That's on an order with what a whole continent-level population uses for electricity these days. Let's say it only needed to push ice at 1 kilometer a second of delta V to get it shoved to a good trajectory to hit the target planet some decades later. And we'll be kind about the rocket equation there and just say 1 megajoule is needed per liter of water, or a kilogram of ice, be it water or frozen methane or ammonia. At 1 trillion watts of propulsion, that means you are importing 1 million liters or 1,000 cubic meters of water a second. That is pretty good. That's going to fill some domes up real fast. But it also means an Earth-sized planet with a surface area of 500 million square kilometers will get only 63 micrometers of new rain in a year, and take 16,000 years to get 1 meter of water down. And that was assuming that was all water ice. By default, Kuiper Belt objects are a mix of water and rock and a smaller percent of ammonia and methane. It varies, we don't have good data on the average yet, and that would vary by solar system too, but figure on getting half that mass in water and maybe 1/10 each ammonia and methane. Those other two will turn into gas, of course, and break up under the ultraviolet light of the local sun, where we'd expect the methane, made of 1 carbon and 4 hydrogen, and ammonia, 1 nitrogen and 3 hydrogen, to end up as carbon dioxide and nitrogen gas, with the excess hydrogen turning into water when exposed to oxygen in the air. You never need to import oxygen, it's the most plentiful element in rock, and you can just melt it out, though that takes more energy than getting it from water if there's water or ice already there. You probably do not want tons of free hydrogen lying around your planet either though, so producing local oxygen is probably a good idea. You might import straight hydrogen from local gas giants too. It's only 11% of water by mass, 89% oxygen, so folks with a big fusion economy or orbital solar arrays might decide to just import that hydrogen and produce oxygen locally. You still need nitrogen, and it's a bit dubious if a planet will have much of a supply. We don't really care about which things we need to bring in and the method for today. We're just emphasizing that there's a timeline involved here, dictated by the sheer scale of the effort needed to move all the seas and sky a whole planet needs, and several billion kilometers at that. Space is big, and icy rocks will be deep out in space. Pushing ice is a multi-decade process too. Those first couple decades are only bringing in water via high-powered spaceships, not low-energy transfers, so it's probably just fulfilling the cisterns needed for that early population of humans already used to recycling water from their long voyage in space. Unless you're settling in a place like Venus or Mercury too, if it's got enough gravity to want to live on, it probably does have decent ice deposits, and it might already have water and air or even too much of one or the other, just depends on the planet. Your lowest hanging fruit for building a biosphere quickly is some planet that already has seas and air, regardless of if it's oxygen rich. We could probably kick tanks of algae and microbes off an airplane over various parts of that planet, probably down along the coastlines, and just wait a few years for the planet to turn into one big algae bloom. Though of course you'd be doing repeat trips and adding in new strains of microorganisms and smaller animals as you went. If there's no life on that planet already, there's no soil, and simply dropping water on it very fast isn't helping much, as it would just mudslide the whole planet. So slow is not bad. The reverse is true for air, particularly oxygen, as the reason it took so long for life to produce an oxygen-rich atmosphere is that photosynthesis and sugar production doesn't produce much of a surplus of free oxygen. Only a little carbon gets sequestered this way, and that oxygen usually gets absorbed by iron deposits, which were regularly churning up on the timelines available. millions of years. You need to be producing your atmosphere, particularly your free oxygen, much faster than this tiny photosynthesis surplus did, so that you're doing it faster than your surface is absorbing oxygen, especially if that surface is getting churned up a lot by you dropping ice balls and torrential rains down from orbit. You may need to keep producing it for a while too when the main work is done at a rate to keep up with geological turnover. An Earth-scale planet needs about 10 to 18 kilograms or a billion megatons of oxygen in its atmosphere. It takes on the order of 10 to 20 megajoules to liberate 1 kilogram of oxygen from regolith. If it was only using 10 megajoules per kilogram of oxygen, then you need to pump in 10 to 25 joules to get your breathable atmosphere, and even more the longer you take, since the ground is leaching it out. So figure out at least double or triple that figure. If triple, your terawatt reactor we mentioned from earlier is pumping out 1 trillion kilograms a year, just a millionth of what you need, and probably not fast enough to overwhelm the rate oxygen is getting absorbed at. For folks curious about the math on that, if you were bringing a new terawatt worth of reactors online each year though, or an oxygen production rate of n gigatons per year, where n is the year, your formula would be n plus 1 times n divided by 2, or the square root of 2 times the square root of 1,000,000 in this case. That's 1,414 years, assuming no leakage, and you wouldn't even get up to 10% of your desired oxygen until year 447. You get to the 30% mark at 745 years, and the halfway mark at year 1000. And somewhere in between those points you could actually breathe the air for short stretches, and you could also expect to be able to have large animals that could be minimally tweaked, possibly just by natural selection, to survive this. You might take Earth-conditioned domes and slowly lower the oxygen concentration in them over the decades to have the animals in them adjust to lower oxygen content until you reach a happy medium of what they've adapted to and what your planet has reached. You might even use some quasi-airlock to let animals move in and out of a dome freely, and see some interesting adaptations of lungs, akin to whales adapting to live mostly underwater but breathing air. But assuming that very optimistic and exponential oxygen production rate, that's still centuries of dome living, followed by centuries of a breathable if weak atmosphere, with each generation moving just a small percent closer to their goal, and each of those will have its own unique culture and traditions, I'd imagine. Think about your country now and a century ago. A lot of change and history happened in that period, pretty much for any country we might consider. Since many animals are likely to handle oxygen better or worse than their cousins, those early ecosystems are going to tilt in their favor and then tilt back when you reach equilibrium. This is also assuming you've been bringing in nitrogen, either liberating it from the local environment or by cometary rain, as it is the majority of our atmosphere. Some planets may already have it in their air too, of course. Needless to say, domes and spinning cans are easier, which is why we talk about using them so much. I don't need to pressurize an entire planet of domes at once, just whichever dome I've built thus far, though keep in mind they'll be leaking too. I would be very impressed by any dome that had a vacuum on the other side and still let sunlight through, and had airlocks for transport getting used regularly that didn't need to completely replace its air at least once a decade. Domes probably only need on an order of 10 kilograms of oxygen per square meter, depends on height of course, whereas an open sky is going to be about 10,000 kilograms a square meter, depending on gravity, as lower gravity planets actually need more air per surface area, and about 2,000 kilograms of that is going to be oxygen. So domes need less than 1% of what open sky needs, and we tend to assume you don't dome everything over. You might, though, slowly build your domes out as what we call a walled house, and let their leakage create your atmosphere, and you slowly stop replacing them. We can already make diamond, it is just carbon, and I would not be surprised if by this century's end we could make diamond windows economically, and some dome made out of it could plausibly go unreplaced for several millennia. This is one way you might be building your biosphere then, not by incremental approach to Earth conditions, but just by bringing each dome online with the right mix of air already in it, and then just shoveling in soil from big vats you were slowly churning the contents of while adding crushed regolith and water and letting the algae and microbes at it. You get soil out of that vat, or a precursor you could process with a different set of microorganisms. This is obviously a process best left to automation, but if we imagined your typical dome needing about 1 ton of wet soil per square meter or yard, and we wanted, say, a hectare per person, or a couple acres, between food production, lawn, garden, and creating a planetary ecology, including wild space, then a given person needs to move about 10,000 tons of regolith and water to those vats and then to those domes in their lifetime. That is inside the zone of good old-fashioned elbow grease with a shovel and wheelbarrow, though it would likely be a full-time job for at least a year. Even in lower gravity, you're also building the dome and its floor. That area could devote a relatively small portion of its surface for solar power to be used to power rock crushing and burning oxygen out of the regolith. So while I can't imagine why folks on another planet would be limited to only modern tech and power production, let alone manual labor for moving rocks, it would actually be possible for them to keep terraforming if they got shoved down the technological or industrial ladder. Or if someone decided to send prisoners to terraform planets and had them smashing rocks with sledges on old-fashioned chain gangs. I think I could see that easier than technology loss. But that too is plausible in some ways, given how hard it is to maintain an industrial base with a small population and a fairly hostile world, especially given that you begin without such a base. On the flip side, you might be doing this far from a sun under artificial light where powering your ecology is the hard part, and volatiles, water, ammonia, methane, carbon dioxide, and nitrogen are super abundant, such as in a space habitat built inside a comet or icy body or on a dwarf planet like Pluto. Space habitats are something of an in-between case because you are presumably filling it all at once. Nothing is stopping you from having a dome inside an O'Neill cylinder, but I would tend to assume you would fabricate these entire structures and only afterwards move folks in, rather than getting in the way of the biologists and their robots. That's a bit of a guess though. The good news is that we almost certainly won't build anything O'Neill cylinder scale until we had already built dozens, if not hundreds, of smaller scale habitats in the Kalpana 1 to Stanford Taurus range, and those are much easier to fill, but also more challenging to keep a decent sized ecology in. At least in terms of larger flora and fauna, you could keep a fairly complete microbial ecology inside some glass bubble or donut of beach ball scale floating in the vacuum of space and turning just slow enough to churn the contents somewhat and provide a meaningful up and down. And you might make things like that as your minimum units that you are building outside of space habitat while it was getting its core landscaping done. Then you dump them in there as the equivalent of buckets of muddy soil precursor and introduce your next step of ecological construction. How fast can you go? Hard to say. I wouldn't want to rule out the ability to construct a space habitat down to the lawns and gardens in under a year, especially if this was a factory-style process, as it might be in our solar system in a few centuries' time. You might mass-produce soil with some fiber equivalent of rebar in it to prevent erosion till plants took root, and have actual tree farms and nurseries that were bringing in trees already a few meters tall to plant. That sounds like an insane use of brute force engineering, but keep in mind the scale we've already discussed today. If you can move mountains, you can move a forest. This is all a long way off still, and as we explored our episode back in the summer, Gardens of the Moon, we have a lot of hands-on experimentation to do in lunar and Martian regolith before we can try much of this out with any certainty. I tend to suspect we'll have a spin-gravity space station and a permanent moon base before we get to 2050, and both will let us begin gathering useful data. Of course, this is only examples like the Moon and Mars, and with Earth-like biology in mind. As mentioned, we might find plenty of worlds with the right stuff already there, and we might want to engineer environments for subsurface oceans below the ice, for icy moons like Jupiter's Europa, or for naturally floating ecologies in the skies of Venus, where floating domes might give way to engineered floating or flying coral reefs on which life clung on. Our focus may have been Earth-like ecologies today, and indeed we really mean those in and about humans, as Earth is full of fairly alien biologies in the deep sea and other strange and hostile niches. But in the future, we may wish to build truly novel or alien biospheres, or adapt our organisms to exist in an alien environment, or some halfway point between what that planet was and what Earth is. The sky's the limit when it comes to strange biospheres we might forge on new worlds, at least so long as you don't mind building the sky too. Today we looked at building biospheres under alien suns for civilization to spread away from Earth and out among all the stars in our galaxy. But what do we do when all those stars die off and no new ones form? What will the universe be like trillions of years from now when all the stars are gone? And is there a pathway forward for civilizations in a dark, post-stellar era? And what does that look like? We'll leap into a distant future of post-stellar civilizations in our monthly exclusive episode on Nebula, the largest creator-owned streaming service, which has tons of extra content from myself and many other creators, including a new full-length episode of SFIA like Post-Stellar Civilizations that we release on the first day of every month. And every episode of the show also airs on Nebula a few days early and ad-free, no random commercials or built-in ads like this one. Using my code, IsaacArthur, you can get 40% off and join for about $3 a month, about the price of the drink or snack you've been enjoying during the episode. We also now have lifetime memberships, gift memberships, and gift cards available to let you share Nebula with friends and family. When you sign up my link, go.nebula.tv/IsaacArthur, and use my code, IsaacArthur, you not only get access to all the great stuff Nebula offers, like post-stellar civilizations, you'll also be directly supporting this show. So today we talked about building biospheres on new planets, and next week we'll look at a spaceship design for reaching other planets, the Medusa Drive, a spaceship design that uses nukes to pull a ship forward. Then we'll ask how technology might permit more off-the-grid living in the future, or allow remote settlements on new worlds. After that, we'll explore another far more theoretical spaceship design, as we see what science has to say about gravitic spaceship propulsion. If you'd like to get alerts when those and other episodes come out, make sure to hit the like, subscribe, and notification buttons. You can also help support the show by becoming a member here on YouTube or at Patreon, or check out other ways to help at isaacarthur.net. Until next time, thanks for watching and have a great week.